Chapter 6, Program Analysis and Design. Our goals for this chapter are to learn about the Software Development Lifecycle, otherwise known as the SDLC, to learn about object-oriented program design, to study the relationships between classes, and to take a look at program efficiency or analysis, otherwise known as efficiency. The software development lifecycle truly is a life cycle. We start with a problem. Every software project is started with a problem, and then we develop a program specification. What can we do to solve that problem? What does the solution require? Then we develop the program design. How are we going to get from point A, where we are, to point B, the solution? If your program design is specific and clear enough, it makes your program implementation phase somewhat straightforward and simple. Program implementation is where you write the code to solve the problem that you've defined and designed a solution for in the program design phase. Then you do testing and debugging, making sure it doesn't have any errors. Then you can deliver it to your user, and then you start your maintenance. Maintenance takes the bulk of the time, and inevitably new technology is going to come along, problems are going to occur, and you will find yourself back with a problem again, and a program specification, and a program design. So it is an iterative process, it's a life cycle. The waterfall model, illustrated on page 222, shows how the one phase flows into the next phase. So program specification flows into design, which feeds implementation, and so on. The waterfall model is a useful way of looking at the software development lifecycle, and we'll see some differences as well. So program specification is a written description of the project, so make sure you write it down. People are going to change their minds, people are going to disagree later, so it's really a good idea to have a written specification of what exactly your solution is going to do. This is always based on customer requirements. Whoever it is that you're writing the code for, that's your customer. So what is it that they need? And it's very important to begin with the end in mind. What exactly does your program need to do? What is the solution? What does the solution look like? The program design, it's essential to plan before you start writing code. Write down what you are going to do and be as detailed as possible. Include all objects, classes, and data structures. And pseudocode, flowcharts, UML diagrams are very useful in this phase. So planning what you're going to do. And many programmers get frustrated. They want to jump right to the code. Let me at the code. I have been involved with many a software development project where the design phase was given the bum's rush, if you will, and you can't write code to solve a problem if you haven't designed that solution first. I mean, our programs are pretty straightforward. They're not as complex as say, designing Snapchat, but if you are writing a large project, a large software development project, it's easy to get distracted and it's easy to get off task. This program design helps you stay the course and not get distracted by other things. When I was, many years ago, when I was working for the military in Hawaii, I was not involved with this project, but we got a lot of good stories out of it. The Navy paid millions and millions and millions of dollars to automate their healthcare system, and it was a disaster. It was a complete disaster. So I think that they probably gave a rush job to the program design phase and needed to do more work there. Program implementation, this is where the design is turned into code. With a good design, this phase isn't going to take very long. So spend your time in the design phase, and the implementation phase will be a breeze. Testing and debugging. It's essential to test. I'm an end user for a pretty large software rollout, not at Xavier, but elsewhere, and using it just the other day. There's a field to enter an email address, and it's restricted to 15 characters. Now think about your email address. It's likely longer than 15 characters, especially at brophy-broncos.org, at xaviergators.org. Those get pretty long. So this was really a flaw in the testing and debugging phase. Clearly, they didn't test with normal email addresses. So make sure that you test. And it's impossible to test for all user inputs because the user is going to behave in ways that you cannot anticipate. I told you about the users using the CD tray for a cup holder. I mean, users are going to do all kinds of crazy stuff, and you're going to wonder, why on earth did they do that? But make sure that your test data includes all lines of code so that you are testing all lines of code. You should test endpoints. So where are your decision points? In your if statements, test for values that are below your decision point, at your decision point, and above your decision point. Check for out of range values. What happens when you enter a value that's out of range? Check bad data to make sure the program handles it appropriately. And be sure that your set of test data tests all lines of code. Types of errors, we've gone over this probably ad infinitum. Compile time errors are known as syntax errors, where you're violating the rules of the syntax and your program you can't translate your source code into object code or byte code. A runtime error is throwing an exception, array index out of bounds, divide by 0, number format exception. All those are examples of runtime errors. Logic errors are also runtime errors in that they happen at runtime. However, they don't throw an exception necessarily. They get outputs that are not anticipated. So your program appears to work, but it's not reliably producing the correct output. So that's an example of a logic error. Robustness is how we refer to a program that is resistant to unsmart users. So a robust program won't give inaccurate answers no matter what the user enters. It won't crash if the input is invalid, and it won't allow execution to proceed if invalid data is entered. Program maintenance. It's said that 60% of your time and money will be spent in the program maintenance phase. Make sure you budget, if you're ever on software development projects, make sure that you budget time and money for this, because programmers we don't think about it. We think, oh, once I create this app or this web page or this whatever, I'm done. I'm on to the next thing. No. 60% of your time is going to be in that maintenance phase. And you're probably familiar with people who've deployed web pages thinking, I'm done, I've deployed it. But always things pop up, and always those web pages need to be revisited, which is a classic example we can probably all relate to. Clear documentation helps minimize the time and effort spent in maintenance. So if you've documented your code, if you've documented your design phase, that's really going to help your program maintenance phase go a lot easier. Object-oriented programming design blurs the lines of the waterfall model. The steps in object-oriented programming design, we identify which classes are going to be written, we identify the behaviors for each class, we determine the relationships between classes, we write the interface, the public method headers for each class, and we implement the methods. So this kind of blurs that whole program specification / implementation because it's more or less the implementation is a bit of an iterative process as we're fleshing out the implementation there. Identifying classes. When you're looking at a program specification, look for the nouns. Ignore pronouns and nouns that refer to the user. Look at big picture nouns. Other nouns, small picture nouns, might end up as attributes. Take a look at page 224 and look at the examples. There's an example of a program that simulates a game of bingo, which I think is pretty instructive since we've all played bingo and may write the code for that someday. So take a look at page 224, study the bingo example. Identifying behaviors. You can find all verbs in the program description, and those are typically your behaviors. And it's likely that behaviors will become methods. Encapsulation is the process of bundling data and methods that act on that data together. And you're probably familiar with that term because we've used it before. But encapsulation is a vocab word that means bundling data and methods that act on that data together in a class. Looking at the relationships between classes, if it's the is a relationship, it means inheritance. Golf cart is a vehicle. Sedan is a vehicle. So that's an inheritance relationship. The composition relationship is the has a relationship. Weather station has a temperature. Nurse has a uniform. Wrapper classes always implement the has a relationship. Umbel diagrams are used to represent classes, the relationships between classes. We represent classes with rectangles. We use angle brackets with the word abstract or interface to indicate either an abstract class or an interface. We show the is a relationship with an open up arrow. We show the is a relationship that involves an interface with a dotted open up arrow, so a dashed line. We show the has a relationship with either a down arrow or a sideways arrow to indicate composition. And look at the examples on page 226. It shows a nice example of all these different relationships. Implementing classes. There are basically two different ways to implement classes, bottom up and top down. If you are looking at bottom up, for each method in the class, you list all the other classes that are needed to implement that particular method. These are called collaborators. The other classes are called collaborators for the method. A class with no collaborators is known as independent. Develop and test all independent classes first, and then include them in the overall project. So you're developing these classes separately and then bringing them together. Bottom-up development, you write your constructors and then your methods, and they should be added and tested one at a time. With bottom-up development, you always have a driver class that contains a main method that's used for testing, and then it can be discarded later when you deploy your classes. In AP Computer Science, we're not discarding our driver class. We're not bringing our classes into a larger project. They're always self-contained, so we don't discard our driver class. When all independent classes are working, we add them to the final project in bottom-up development. And we continue to create and add classes to build up the application from the bottom up. With top-down development, the programmer starts with an overview of the program. So imagine looking down from a 10,000-foot level. We are selecting the highest level controlling object first, and those tasks needed for high-level control. And during development, other classes may be added to simplify the existing classes, and we'll look at a bit of that abstraction in a minute. So implementing methods. Procedural abstraction is the act of taking repeated code and putting it into a method. So we want to avoid chunks of repeated code. We don't want to be writing the same code over and over for a couple of reasons. One, the more lines of code, the harder it is to debug, modify, and maintain. But two, if we need to make a change in that code, we only want to change it once. We don't want to change it in multiple places. So if you have chunks of repeated code, it's useful to take that chunk, stick it in a method, and everywhere you need to repeat the chunk, call the method. So we take all those lines and put them in a helper method. The use of helper methods within a class is known as procedural abstraction. So we're taking tasks and putting it in a procedural abstraction. The process of breaking a large method into a sequence of smaller tasks is known as stepwise refinement. So if you have a large process, like I have to prepare for the AP exam, breaking it into smaller tasks, like reading the Barron's book, doing the multiple choice problems, doing the coding bat, those are smaller tasks to lead you to the overall goal of studying for the AP exam. Information hiding, declaring instance variables and helper methods as private is the concept of information hiding. It prevents client classes from accessing them. Helper methods are not designed to be used outside the class. And instance variables are not designed to be accessed from outside the class. We need to keep the instance variables private so that we have gatekeepers to make sure that our data doesn't get corrupted. So 99.9% of the time, and I think 100% of the time on the AP exam, make your instance variables private. A stub method is a dummy method that stands in for an actual method until the actual method has been written and tested. So you can develop the rest of your class without developing all the methods, just having a method stand in for it and satisfy the condition. Like, let's say your method needs to return an int, just say return 0 or -1, just to satisfy that condition and prove that you can call the method and keep going. Typically, a stub will produce some output to show that it was called, or it may return a reasonable value. When I'm debugging a lot of code, I might put some output statements in that say, method empty_France was called, which just lets me know that it happened. It just tells me where things are. An algorithm is a step-by-step series of instructions to solve a problem in a finite amount of time. Something's important to know about algorithms: they are repeatable. So anybody can implement that algorithm and come up with the same results. Anybody can go to the recipe book, follow the instructions for making brownies, and wind up with brownies at the end. Same is true for an algorithm. It is repeatable. Other thing about an algorithm, it doesn't take forever. It's a finite amount of time. It's not going to keep going and going and going. And finally, an algorithm works for tractable problems, problems that have a solution. For intractable problems, sometimes a heuristic is useful, but that's beyond the scope of this class. So an algorithm is a precise, step-by-step series of instructions to solve a problem in a finite amount of time. Do not write any code for an algorithm. Do not write an algorithm until the steps are completely clear. You can't solve a problem that you don't know how to solve. You can call an algorithm someone else has written. Like, let's say you don't know how to do a bucket sort, but there's a bucket sort routine that you could call. Sure, you can call that method. You don't have to know how it works. You just have to know that it works. But you can't write your own algorithm until you know how to solve the problem. Absolutely 100%. Know the vocabulary on page 233. It's essential for the AP exam, and I am a firm believer in knowing the vocabulary. Make flashcards, do a Quizlet, whatever it takes, learn those vocab words. Program analysis. Program correctness does not mean that the program runs. It means that it reliably produces the correct output. So testing that a program works does not prove that it is correct. Usually people say, but it works. No, it's telling me that 2 + 2 is 8. It doesn't work. So make sure that program correctness is not the same as runs. An assertion is a precise statement about a program at a given point. If the assertion is proved to be true, then the program is working correctly. Assertions used on the AP exam are preconditions and postconditions for methods. So it will tell us, when this method is called, these are things that are true, the preconditions. When this method is done, these are things that are true, the postconditions. So these are specific assertions. Sorry, I got ahead of myself. Preconditions and postconditions, they are like little gifts to the AP test taker. So you can assume those things to be true about preconditions because they've told you that they are true, which is really handy. You don't have to check for null if the precondition tells you the list contains at least one element or is not empty. Efficiency, you look at two things when looking at algorithmic efficiency. How much CPU time does it use, and how much memory does it use? With CPU time, you want to be as efficient as possible. You don't want to needlessly ask it to compare values. This is why we want to avoid tautologies. A tautology is an expression that is always true. Do not put a tautology in an if statement because you already know the answer. So don't waste the CPU time evaluating that tautology when you already know the answer. And memory, be as efficient as possible with memory. Java's garbage collector helps us with that. But if you create arrays that are needlessly large, or you create multiples of arrays when you don't need to, that's going to chew up your memory. So in summary, learn the vocabulary. Never make assumptions about a program specification. Write it all down. Make sure you're clear about what is required. Always design before coding and make sure that it's written down. And this little doggerel was on the wall of the computer lab when I was in college. I really hate this darn machine. I wish that they would sell it. It never does quite what I want, but only what I tell it. The computer can only do what you tell it to do in the program. So make sure that you understand the solution before you start writing the code.